Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 684, Redundant Connection. In this problem, a tree is an undirected graph that is connected and has no cycles. And we're told that a graph that started as a tree with n nodes labeled from 1 to n with one additional edge added. So we're basically told that our graph was originally a tree and we've added an additional edge, and the added edge has two different vertices chosen from 1 to n and was not an edge that already existed. The graph is represented as an array edges of length n where edges r equals ab, which indicates that there is an edge between nodes a and nodes b in the graph. Okay, so we want to return an edge that can be removed so that the resulting graph is a tree of n nodes. And the trick here is to understand that trees have no cycles. So if we look at a tree, we have there's no cycles. There is no way that we can go from 2 to 3. It's not unidirectional basically. So because of that fact, if we have a cycle, so if we can go from 1 to 2 to 3, so if we see that there is any sort of cycle between in our graph, we know that this is not valid, and that the last edge. So the way we can solve this problem is by actually building our graph, but basically building our graph, and as we go, every time we build our adjacency list, we check for cycles. So if our cycle was to be here, let's say we've got graph 1, actually let's clear that up. So let's say we've got graph 0, graph 1, and graph 2. So from graph 0 to 1 is fine, 1 to 2 is fine, and then 2 to 0 is the culprit. This is where we get our cycle. So we know that the edge that we need to return in the output, sorry, is going to be graph 2, 0. So in this example, it's 2, 3. So 1, 2, 1, 3, and then 2, 3. And we're told, what if there are multiple answers? We have to return the one that occurs last in the input. So basically, we want to return the last element that causes, or the last edge is the two last edges, which, or the last edge, sorry, that causes this cycle to close. So the edge that, if removed, cycle won't exist. So basically the last connecting edge in a cycle. So knowing that this is basically a cycle detection problem, let's look at this example. Removing 5 looks like, oh yeah, this is the one that is anomalous, but it won't do anything really. If we remove 5, we still have a cycle. So how can we solve this? We can remove 1 and 4. So this is the last occurrence of this cycle. Removing this linkage basically means that we don't have a cycle, we end up with a tree. So this is what we do. We could remove a cycle by removing 2, 3, or 1, 2, but this doesn't satisfy the requirements for this question, because we have to return the answer that occurs last in the input. That's 1, 4. We're given some constraints as well, and we're told that the given graph is connected. So let's solve this problem. So we're going to be using depth first search for cycle detection. Before that, we also want a dictionary to build our adjacency list. We're going to set that to dictionary, and each element is going to have a set. And our depth first search function, let's just actually call it has cycle. And it's going to take x, it's going to take target, and it's going to take a visited set. And we're going to say if x is equal to our target, well then boom, we found ourselves a loop, a cycle, so we can return true. Otherwise, we can add to our visited set x, and we can say for each vertice in graph x, if v is not in visited, and has cycle, and then let's pass into has cycle iteratively. So we're going to say for not in actually for v in graph x, yeah, if v not in visited and has cycle, let's pass in v target and our visited set. Then we're just going to return true. Otherwise, if we finish and we don't get a cycle, we're just going to return false. So that's our has cycle function made. Now we can actually go through all the edges and check which one causes a cycle. So we're going to say for x and y in edges. First, we want to actually check is both x and y in the graph, because there's no point checking for a target if that target is not even in the adjacency list. We're going to get false anyway, so we might as well not check. So we're just going to say if x is in our graph and y is in our graph being our adjacency list, and has cycle, I'm going to copy paste this, has cycle, and we're going to pass in x. And our target is going to be y, of course, and visitor is going to be a new set. So in the case that cycle is detected, we're going to return x and y. Otherwise, we're going to add to our adjacency list. So we're going to add x dot add y, and then copy paste this, y dot add x. And then we want to, if we finish this for loop without returning, if we go through all the edges and there's no edge which causes a cycle, so we've got a valid tree anyway, we're just going to return an empty list. So let's submit our code. Let's make sure our solution works, and it doesn't, because collections.default object is not okay. It's not callable. For v in graph x, got it. We are using the wrong type of brackets, so instead of meant to be using square brackets, let's check our code now. And we pass all 39 test cases. So in terms of time complexity, guys, we're going to be doing an O event square time complexity, because remember, we may be doing depth first search for the entire graph worst case scenario, and space complexity as well. Our visited set may contain every single node in our graph worst case scenario. So O of n, space complexity, and time complexity is going to be big O of n squared. With that being said, I hope you guys enjoyed this video, and I will catch you in the next one.